Hi friends, I'm Madhu. This is the presentation of our project Twitter bot detection. Twitter, as we know, is one of the most popular social networking sites, but it has been plagued by bots which try to control the opinion of the public by flooding Twitter with biased tweets. This has motivated us to create a classifier to detect such bots. The first step in creating a classifier is to collect data. Bot data is collected from websites like BotWiki, which has a list of genuine bot accounts, and user accounts are collected from our friend list and verified celebrities. After collecting the data, we need to pre-process the data. The first step in pre-processing the data is to clean the data. We collected recent 200 tweets from every account, but these tweets contain a lot of non-textual data which are like URLs and emoticons, which are removed using NLTK and regex packages. After that, the data is converted into a sparse matrix using count vectorizer. Once the training data is ready, we used multinomial naive Bayes, Bernoulli naive Bayes, and logistic regression for textual classification. After running a tenfold cross validation, we see that the results were meek at the best. This is because bots have evolved and are generating tweets similar to normal user. So we dis- discarded the use of tweets for bot detection and created our own classifier, which my teammate will explain.
Hi friends, my name is Data and I'm going to talk to you about a new algorithm. Before implementing this algorithm, we tried doing sentimental analysis on the tweets and decision trees on the major attributes. We ended up getting a training accuracy around 80%, and that was really sad. So, we tried to make up our own algorithm. Reasons for choosing our algorithm: due to inaccurate labeling in the training bot data, we tried to make up a classifier which identifies the user accounts and then applied the classifier on the training bot data to clean it. Considerations for our algorithm. The best datasets which we had were our personal user datasets and the personal bot dataset. We even tried making use of other attributes of a Twitter account like the screen name, the name, description, statuses accounts, followers counts, and friends counts. The first step of our algorithm dealt with finding the bot phrase in the screen name or the description of a Twitter account. And whenever we found a bot phrase, we changed the value to 2. The value is a parameter which is used for flagging for a bot or a user. But there was a drawback in this step. If a user had a phrase like a bottle or a botany, then also it can be flagged as a bot. We have taken enough measures in the future steps to avoid this false positive. Conclusions from the first step. We can see that the accuracy of finding a bot word in personal user dataset is 0. But there were few accounts in the training user data which had the bot phrase and led to an accuracy of 1.5%. In the bot data, we could easily filter out 58% of our personal bot accounts and around 30% for the training bot accounts. Our second step was to filter a Twitter account with 0 statuses, 0 followers, or 0 friends to be flagged as a beginner user account. When we tried to implement the second step on a personal user dataset and the personal bot dataset, we could just find 2 accounts. When we tried to implement this on a user dataset, we could find around 24 accounts and we could find 250 accounts in the training bot dataset, and these 250 accounts can be considered for inaccurate labeling. The third step deals with the tweets to friends ratio and tweets to followers ratio. Whenever these ratios were less than 12, we recognize them as a common user. When we applied this step on a personal user data, we could identify the user accounts with 100% accuracy. Applying this step on a personal bot data led to an accuracy of 2%. The training user data had an accuracy of 89.7% and training bot data had an accuracy of 16.7%. A fourth step dealt with using the verified attribute. If a Twitter account was verified, then we flag it as users, otherwise bots. Usually, Twitter verifies only users and not bots. When we applied this step on a user data, we could get an accuracy of 52% and 44%. On the bot data, personal bot data had a 0% accuracy, and on the training bot data, we had a 0.6% accuracy. This is another proof to say that the training bot data had inaccurate labels. The fifth step is used to filter out the clever bots. Whenever there was no bot phrase in the screen name or the description, and these bots were even able to filter from the third step. Whenever the tweets to friends ratio and the tweets to followers ratio was greater than 10, we recognized them as the clever bots. Finally, the training accuracy calculation was the user detection on the user data led to an accuracy of 198% and bot detection on the bot data led to an accuracy of 90 and 65% accuracy. We got an training bot data set accuracy around 65% because the rest of the accounts were mostly due to inaccurate labeling. Performance analysis. Our new algorithm had an accuracy on training of around 86%, which was way greater than other previously three implemented algorithms. Our mean square error of a new algorithm is also very low. Receiver operating characteristics. We could obtain much better receiver operating characteristics from a newly implemented algorithm than the previous three. Our future work will deal with acquiring more data with accurate labeling and doing sentimental analysis and friends hierarchy on the acquired more data, and we'll even try to look into the user metadata and the behavior features of the bot accounts. Thank you.